Hi students, welcome to class. Today we're going to be talking about multiplying polynomials, and that just sounds so exciting. We're just going to get right down to business, no warm-up today. So let's talk about our three learning goals. We are going to be multiplying polynomials. We're going to use binomial expansion to expand binomial expressions that are raised to positive integer powers. And that's a mouthful. And we're also going to be using Pascal's triangle to expand binomial expressions. Okay, so when we think about multiplying polynomials, which is that first learning goal, you probably think about times that you multiply polynomials using distributive property or maybe even FOIL. And that is exactly what we're going to be doing here. So this is probably a little bit of a review. And we might have polynomials that are a little more complicated, but this is certainly something that you've done before. So for example A, if I wanted to multiply 4y squared by y squared plus 3, I really just have to distribute that 4y squared to each one of those terms in the binomial. And when I multiply the coefficients and I multiply the variables, which means that, and you can multiply anything. Remember, we could only add and subtract like terms in polynomials, but we can multiply anything. And so when we multiply, the exponent on the variables are going to change. And when you multiply bases that are the same, you always add the exponents. So to multiply 4y squared by y squared, I'm going to get 4 times 1, which is 4, and then y squared times y squared, which is y to the 4th. And then 4y squared times 3 would give me 12y squared. I mentioned that some of these will be much more complicated polynomials. So and that's exactly what you see in B. So this just requires that you be really organized when you're multiplying, and just be really careful with watching for things like that. If you have a variable that doesn't have an exponent, it really means it's a 1, things like that. So to multiply fg by this polynomial, this kind of mess. Again, I'm just going to distribute, just do a little bit at a time, and then at the end I'll look for like terms to add together. In our last example, we didn't have any like terms. They had two different powers on the variables, so I couldn't combine them. That might occur here. We might be able to add some like terms. So first thing I'm going to do is actually multiply. So fg times f to the 4th will be f to the 5th times g plus, when I multiply it by the next term, I have 2 f to the 4th power, because I have the f to the 1st and the f to the 3rd, and then g squared. G to the 1st and g to the 1st is g squared. Then I distribute it to the minus 3 f squared g squared, and that will give me a minus 3 f to the 3rd g to the 3rd. And then finally distribute it to the fg to the 3rd. I'll get a plus f squared g to the 4th. Now I want to go back and look and see if there's any like terms. Well, to be like terms, we have to have the exact same variable or combination of variables raised to the exact same powers. And clearly that's not the case here. About the closest we get is this term right here, where we have 2f to the 4th and g to the 2nd, and that, you could kind of maybe accidentally confuse this f squared g to the 4th as a like term, but the f has a power of 4 in the first monomial, and in the second one has got an f squared. So right away we can tell we can't put those together. So they're not the exact same variable or combination of variables raised to the same power. So they're not like terms, and so that actually, I like that, because that means I have less to do, and my final answer then is just this. Now when we have variables kind of mixed in, two different variables like that, we sort of don't always follow the rules of putting them in descending order of powers necessarily, but if, I guess technically what we'd want to do is put the highest degree first. But really, in this case, it really doesn't do you a lot of good, because in this case, each one of the terms has a degree of 6, because, like you look at this first one, this first term right here, f to the 5th, g to the 1st. Remember that to find the degree of a monomial, you add the exponents. So this actually has a degree of 6. This next one has powers of 4 and 2, so it has a degree of 6. The next one's 3 and 3, so it also has a degree of 6. And again, so does the f squared g to the 4th has a degree of 6. So it really isn't going to do you any good to move it around. They're all the same degree anyway. So in general, to multiply any two polynomials, you use the distributive property and multiply each term in the second polynomial by each term in the first polynomial. And keep in mind that if one polynomial has m terms and the other has n terms, then the product has m times n terms before it is simplified. In other words, before like terms are put together. So that's just a nice way of being able to check to make sure you got all the multiplications you had to do, because like in this first one I had, let's see, 1, 2, 3, I'm sorry, not the first one, this B, I had a 4-term polynomial and a 1-term polynomial, and 1 times 4 is 4, so when I did my multiplication I had 4 terms. And you know, if there were things I could do to group them together, then my final answer might be have less terms if I can combine ones, but in the intermediate step we should have m times n, meaning the number of terms in the first polynomial times the number of terms in the second polynomial, that many of terms. And that just kind of helps us to make sure we did all of the multiplications, and we didn't just like skip one of the distributives that we needed to do. So keeping that in mind for example 1b, if I want to find the product of a minus 3 times 2 minus 5a plus a squared, I have a 2-term polynomial. I'm going to be multiplying it by a 3-term polynomial. So before any like terms are added, I should get 6 terms. So we'll just kind of a little mental checklist. So first of all, what I like to do here is if I have a polynomials that only have one variable, I like to put them in descending order of powers right from the start before I multiply. And so that's okay with this first, this binomial, it's in descending order, but the other one's not. So I'm going to go ahead and rewrite it in standard form so that the a squared comes first, then minus 5a, and then plus 2. And now I'm going to distribute and multiply horizontally. So when we multiply horizontally, basically we're just going across like our normal way that we do that from left to right. So I can multiply the a by the a squared, the a times the minus 5a, and the a times the 2, and that's going to give me a cubed minus 5a squared plus 2a. And then I can move on to the next term, which is the minus 3. And I'm going to distribute that minus 3 through to each of these pieces. And then I get minus 3 times a squared, which is minus 3a squared. Minus 3 times minus 5a is positive 15a. And then finally minus 3 times positive 2 is minus 6. So there's that those 6 terms I talked about earlier, but now we can add the like terms together. So let's see, some like terms we have, we have an x cubed, and there's only one of, or I'm sorry, a cubed, and there's just one of them. So I write that first, and then I take a look to see, do I have more than one squared term? And I do. There's this one and this one, and when I combine them together, I get minus 8a squared. And then the a terms, there's that and that. When I put them together, I get 17a. And then the constant terms, there's actually just one of them, and that's a minus 6. So my final answer is going to be a to the third minus 8a squared plus 17a minus 6. And that would be in standard form in descending order of powers. Now that really is my preferred way to multiply polynomials, but there are kind of schools of thought out there that some people do well with a vertical method, and so I want to show you that one as well. You don't have to do that this way. I'm just going to show you that so that if this kind of appeals to you, you could use this method. So when you multiply vertically, basically what you do is I usually will write the larger polynomial, the one with more terms first on the top. So I would write a squared minus 5a plus 2, and again I like to put those in the descending order of powers first, and then I'd write below it the a minus 3, and then I'm multiplying. So I multiply by first taking the negative 3 and multiplying, so basically just take this 3 and multiply it by each thing in order. So I'll go the negative 3 times the 2, the negative 3 times the negative 5, the negative 5a, excuse me, the negative 3 times the a squared. And that's going to give me, let's see, negative 6, and then positive 15a, and then negative 3a squared. And then I look at the other term, and I'm going to multiply those through. So I take the a and multiply the a by the 2, the a by the minus 5a, and the a by the a squared, and then I write that below it. So, and then what I try to do is I line up the like terms. So if I multiply the a times the 2, that's going to be 2a, so I'm going to line that up below the 15a. And then the a times the minus 5a is a minus 5a squared, so I'll put that below the a squared term. And then the a times the a cubed, there's not an a cubed above it, so I just write the a cubed up front. And then when I add the like terms, they're sort of right above each other. And so then the leading term will be the a cubed. And then the minus 3a squared and the minus 5a squared is minus 8a squared. The 15a and the 2a add to 17a, and then the minus 6. So of course we do get the same thing. It doesn't really matter which method you use, you're going to get the same answer. So you can choose whichever way appeals to you. And maybe this is a new way, maybe you've never seen it done this way, and if you like it, give it a try. So let's move to the next page. And we are going to make this one a you try question. You're going to get a chance to multiply this one out on your own. So please take some time, pause the video now, and multiply. Find the product of these two polynomials. Okay, so take some time to check your answer very carefully. Make sure that you have the correct powers, coefficients, and then, of course, that you've written it in standard form at the end. Okay, let's take a look at an application. A standard Burley box is p feet by 3p feet by 4p feet. So we've got this box, and I just did a little quick sketch of a box. And the dimensions, the length, width, and height are p, 3p, and 4p. So it doesn't really matter which one you label which, but so I'm going to call the longer one I drew 4p, and then I'm going to make this one over here be 3p, and then I'll make the height be p. So length and width 4p and 3p, and the height p. And it says write a polynomial. Oh wait, and then I'm sorry, a large Burley box has 1.5 feet added to each dimension. And so each of these dimensions would be increased by 1.5 in this larger box. Write a polynomial v of p, so we want to call it v of p, in standard form that can be used to find the volume of the large Burley box. Okay, well, if I wanted to find the small Burley box, I think about the one that we've got right now, the standard. We know the volume is found by multiplying the length, the width, and the height. So that would just simply be multiplying the 4p by the 3p by the p. Okay, this is for the standard one. And so that would be, let's see, 12p cubed. But this is for standard. This is the standard one. But if I were to add 1.5 to every one of these dimensions, that's going to actually make my calculation of the volume much more complicated, because now the volume is going to be the length, which is 4p plus 1.5 times the width, which is 3p plus 1.5 times the height, which is p plus 1.5. It just looks more complicated, but it certainly is something we could do using what we know about how to multiply polynomials. But this time we have 3 polynomials. So what do you do when you have 3 polynomials? Well, multiplication is an operation that is designed for 2 terms, numbers, whatever, only. So we can't actually multiply all 3 of these dimensions at one time. We could multiply the first 2 binomial terms. We could multiply these 2 right here, and then whatever we get, we could then multiply it by the last one, or we could multiply the last 2, and then whatever we get, like I can multiply these 2, and whatever I get, multiply it by 4p plus 1.5, and whatever you decide to do. So for this particular one, I am going to multiply the second 2. So the 3p plus 1.5 and the p plus 1.5, and then whatever I get, I'm going to distribute the 4p plus 1.5 through. So let's go ahead and dig into that one. So when I have two binomials like this, I could use FOIL. I mean, that's really just distributive property, so you can certainly do that if you want. So the first two would be the p and the 3p. That makes 3p squared. The two outside, that's 1.5 times 3, and that's 4.5p. And then the two insides, I get a 1.5p. So again, I'm just doing first outside, insides last. The last two, 1.5 times 1.5 is 2.25. Now I can put some like terms together, so I'm going to go ahead and real quick group these two. They're both terms with p, so I'm going to put those together. And so I have 3p squared. And when I add the 4.5p and the 1.5p together, I get 6p, and then plus 2.25. And then I got to bring down this other binomial, and now I'm going to have to distribute it through. And just in the interest of saving a little bit of time on the video, I'm just going to tell you what the right answer, or the final answer is going to be, but that's going to basically come from just taking the 4p and distributing it through, and then taking the 1.5 and distributing it through and adding the like terms. And it turns out that this is what we get for our final answer. 12p cubed plus 28.5p squared plus 18p plus 3.375. So that gets pretty complicated, and again, the suggestion I just make is try to be as organized as you can, and just make sure you've combined all like terms at the end. So let's move on to look at our second learning goal. So our second learning goal involves expanding a power of a binomial. So in example A, we're asked to find the product a plus 2b to the third power. So that means this whole quantity, this sum, a plus 2b, we want to raise it to the third power or multiply it by itself 3 times. So what that would actually look like in expanded binomial form is a plus 2b times a plus 2b plus a times 2b. So just as in the prior example, it got pretty complicated because we were multiplying 3 binomials. That is exactly what we're doing in this example as well. But what maybe complicates the issue a little bit here is we also have 2 variables, whereas in the prior example we just had p. So probably the best way to approach this is to, and we're going to look at other ways, but for something that's a low power like 3, if we're just multiplying 3 binomials, is really just to multiply these out by picking 2 binomials to start with. So let's say I pick and I can pick, any 2 of these to work with first, but I'll show you for a reason why I always pick the last 2. And I'm going to FOIL these out. And then whatever I get when I FOIL, I'm going to multiply by a plus 2b again. So I'm going to bring this binomial down, and I'm going to multiply the last 2 here using FOIL. So when I multiply the first 2, the first 2, a times a is a squared. Okay, the last, or the outside 2 would be plus 2ab. And the inside 2, again, 2ab. Now the reason why I put the a first and then the b is it's just usually it's typically done where you put them in alphabetical order, and then it also makes it easier to see when you have like terms. And then the 2 last terms, 2b times 2b is plus 4b squared. So I have some like terms here. So my like terms are the 2ab and the 2ab. Those are like, so I can put them together, and when I combine them, they give me 4ab. So it turned out that those 2 binomials multiplied gave me a squared plus 4ab plus 4b squared. And now the last thing I need to do is then go ahead and distribute the a plus 2b to this polynomial. So I'm going to distribute the a through to everything. See what I get? Well, a times a squared is a cubed. A times 4ab is 4a squared b. A times 4b squared is 4ab squared. And now I'm going to go ahead and I'm going to distribute the 2b through to everything. And then the final thing will be to check to see if I have any like terms. So 2b times a squared is 2 plus 2 a squared b. Then the 2b times 4ab, and that would be 8ab squared. And then finally the 2b by the 4b squared, and that would be plus 8b cubed. Now the last thing I need to do is kind of scan through this and see if there are any like terms. So if I had an a squared b and then I had an a b squared, those are not like terms. But if you look here, I have a 4a squared b and I have a 2a squared b. So those are like terms. And I also have another set of like terms. I have 4ab squared and an 8ab squared. So those are like terms as well. So once I put those like terms together, I don't have any other a cubed, so it's a cubed. If I put the a squared b terms together, I have 4 of them and 2 more. That makes 6a squared b. Once I put the ab squareds together, I have 4ab squared and 8ab squared. They add to 12ab squared. And then finally, I don't have any other b cubed terms, so that's 8b cubed. And that is my final answer. And that's a lot of work, and there are lots and lots of opportunities to make errors there, whether it be when you're multiplying and you might have had the wrong exponent, or if you didn't see that you had like terms or whatever. So this really, again, takes a lot of organization, and there are lots of opportunities to make errors when using distributive property to do this. Now, so because of that, we are going to introduce a couple other methods of expanding out binomials, because you think about how that was pretty difficult and we just had 3 binomials to multiply. What if we had a binomial to the 4th power or the 5th power, and now we had to do this multiple times? So it could get very cumbersome. And so we're going to go ahead and take a look at a couple methods that might make things a little bit easier here. So let's go ahead and turn the page and take a look at those methods. Now normally we might give you example B as a you try problem, but you can see again how involved that last example was. So I'm not going to do that to you, but instead I'm going to go ahead and introduce to you one of the other methods that we can use to expand a binomial, and it's going to involve using a part of what's called Pascal's triangle. So let me give you a little introduction to Pascal's triangle. First of all, Pascal's triangle is one of the most interesting number patterns, and it's named after Blaise Pascal, who was a famous French mathematician and philosopher. He created this triangle starting with a 1 at the top. And to build the triangle, he started with 1 at the top and then continued placing numbers below it in a triangular pattern, where each number is just the 2 numbers above it added together, except for the edges, which are all 1. See, for example, if we started with 1, and then to get the numbers on either side below it, we just added the numbers directly above it. Well, there's directly above this one, there's a 1, and then over here, there's actually really a 0. So if you can kind of think about these being zeros out here. And then, so basically that pattern really is very apparent once you get down further in the triangle. But for instance, for this the ones on the edge, again, each row starts out with a 1, so I have a 1, and then this 2 comes from adding these 2 ones above it, and so I get 2. Then I drop down to the next row, and this 3 comes from adding the 2 above it. The 1 and the 2 from the row above it make 3, and the same thing here. And then of course they begin and end each row with a 1, which is, again, is still meeting the pattern. It's just kind of like there's a 0 out here, and so I'm adding the 1 from above it, and this 0 that's sort of that's not really out there. It's just kind of, this, I'm going to have to edit this out. It's this, yeah, whatever. So anyway, then each pattern as you go down, and if you look at the next row down, the 4 comes from the 1 and the 3 above it. The 6 comes from the 3 and the 3 above it to the left and to the right. And then again the 4 from the 3 and the 1 above it to the left and to the right. And So that pattern continues on and on and on. And actually, we're going to go ahead and see if we can understand that pattern by filling in row 6 and 7. So as we said earlier, every one of the rows starts with a 1. So row 6 would start with a 1 as well. The next term in will come from the sum of the two numbers right above it, and so that's going to be a 6. The ones right above the next space are 5 and 10, so they add up to 15. Then the next one, 10 and 10, they add up to 20. 10 and 5, again to 15, and 5 and 1 add up to 6. And then finally we end with a 1. So let's pause the video for a moment and give row 7 as a you try. You try to fill in the rest of Pascal's triangle up through row 7. Okay, so that final row was 1, 7, 21, 35, 35, 21, 7, and 1. And this pattern can continue on and on and on. Now it turns out that there's some really interesting connection between the coefficients of a binomial when it's expanded and Pascal's triangle. And so we're going to actually look at two ways to use rows of Pascal's triangle to help us expand binomial expressions in an easier way than the way we just prior looked at. All right, so we're going to go ahead and take a look at example B. Find the product 2x minus 1 cubed. Now notice I crossed out the directions or the steps to the right hand side, and those basically directed you to use the method of the prior example where we used FOIL and the distributive property to multiply the three binomials. Well, in this particular method, we're going to use a method that was developed actually by a student much like yourself in an Algebra 2 class. In fact, if you look in the online textbook or if you have a paper textbook on page 417, you'll see a box that's called Student to Student. And in that box, a student, Caitlin Humphrey, shares her way of expanding binomials using Pascal's triangle. And what she does is she makes a 3-row table. And in the first row, she puts the numbers from Pascal's triangle that are associated with the power that the binomial is being raised to. So in this case, that means the row that's associated with 3. So that's row 3. So if we look at row 3 down here in Pascal's triangle, the numbers in that row are 1, 3, 3, 1. So those are the ones that we're going to put in our first row of our table. So we're going to write 1, 3, 3, 1. Now in the second row, we're going to put descending powers of the first term. So the first term is this 2x, and by descending we mean starting at the highest power and going down. And so what power we actually start at is that 3. So we're going to put in this first spot, we're going to put 2x raised to the third power. So if we were to raise 2x to the third power, that would be 2 to the third and x to the third. So that's 8x cubed. So we're going to put that right here, and then we're going to go in descending powers. So in the next spot, it would be 2x raised to the second power, which is 2 squared, which is 4, and x squared. And then we're going to put in 2x raised to the first, which is 2x, and then finally 2x to the 0 power, which is just 1. In the third row, we're going to put ascending, meaning starting at the lowest and going up, ascending powers of the last term. So the last term is this -1. And so we're going to start by raising -1 to the 0 power, which is the lowest power. So anything to the 0 power is just 1. And so that first spot is going to be filled with 1. And then we go up from there. So -1 to the first power is -1. -1 raised to the second power is a 1, because -1 times -1 is +1. And then finally -1 raised to the third power, which is a -1. And again, we're stopping at 3 because that's a third degree expansion that we're doing. We're raising something to the third power. So the final step to get our expanded polynomial is to just simply multiply down each one of these columns. And when we're done with this multiplying down the columns, we'll have our polynomial completely expanded out, all like terms added together, and nothing more to do. So the great thing about this is we're not searching around, looking at all the terms, seeing if there's ones that we can group together that are like terms. It's all been done through this table. So let's multiply down the first column. 1 times 8x cubed times 1, that's 8x cubed. Then down the next column, 3 times 4x times -1 is -12x squared. Down the next column, 3 times 2x times 1, that's plus 6x. And then 1 times -1, that's -1. And that is 2x minus 1 raised to the third power in expanded form. Now, just to show you that that really works, what I'm going to do is I'm going to redo example A that we did back on this prior page right here. Okay, this one, this A plus 2B raised to the third power, and we're going to verify that we get the same answer using this method. Okay, so A plus 2B to the third power. So I go to Pascal's triangle, I get the correct line of numbers, or row of numbers, and that's, again, the 1, 3, 3, 1, because I have a power of 3 again. So 1, 3, 3, 1. Okay, in the second row, I go descending powers of the first term, so starting at 3. So the first term is A, so I'm going to start at the highest power, A to the third, then a squared, then a to the first, and then a to the 0, which is 1. And then I go in the last row, ascending powers of the last term. So the last term is 2b, so I'm taking 2b and I'm going to start at raising it to the 0 power, which is 1. Then I'm going to raise it to the first, which is 2b. Then I'm going to raise it to the second, so that's 2 squared and b squared. That's 4b squared. And then 2b to the third, so that's 2 to the third, 8. b to the third, that's b cubed. And now I'm going to multiply down my columns, and then I'll turn back to the prior page and we'll compare and make sure we got the same thing. So 1 times a cubed times 1, that's a cubed. 3 times 2, which is 6, times a squared times b, that's 6a squared b. Then down the next column, 3 times a times 4b squared, that's 12ab squared. And then finally down the last column, 1 times 8b cubed, that's 8b cubed. So let's take a look back. I'm going to circle that. Look what we've got. A to the third plus 6a squared b plus 12ab squared plus 8b cubed. So if we turn back to the prior page, let's see if we get the same thing. And sure enough, there it is. A cubed plus 6a squared b plus 12ab squared plus 8b cubed. Same thing. Here's the work here by using FOIL and distributive property, and here's the work using our little table. Okay, so let's turn the page, and you'll notice that this table just shows us some different binomial expansions of the binomial a plus b. So that's just sort of a random generic binomial a plus b. It really could be any binomial, but if you raise a plus b to the 0 power, you get 1. If you raise a plus b to the first power, you get a plus b squared, you get this, and so on. And what you might notice is that this little table looks an awful lot like Pascal's triangle. And in fact, if you were to write in the coefficients that they left off, because they leave off the ones, that if you just looked at those coefficients, they actually are the numbers from Pascal's triangle. So like for instance, row 3, there's that one we've been using a lot, the 1, the 3, the 3, the 1. The next one is 1, 4, 6, 4, 1, and so on. And you can, clearly see that pattern showing up here in this table. And so if I wanted to, say, add the next row into this table, and I wanted to expand out a plus b to the 6th power, I could actually just use the method that we just looked at with our little table that we make. And so if we went back and we looked at line 6 or row 6 from Pascal's triangle, it would look like this. It would be 1, 6, 15, 20, 15, 6, 1. And just flip back and show you that. It's right here in the Pascal's triangle, 1, 6, 15, 20, 15, 6, and 1. And then the way our expansion method works is we then take the first term and we go in descending order of power starting at the exponent, which is 6. So this next row would be a to the 6th, a to the 5th, a to the 4th, a to the 3rd, squared, a to the 1st, and a to the 0, which is 1. And then we take the last term, which is the b, and we go in ascending order starting at b to the 0, so that would be 1, b to the 1st, b to the 2nd, 3rd, 4th, 5th, and 6th. And then we could just simply multiply down the columns, and we would get a plus b raised to the 6th power in expanded form. So if I multiply down the first column, 1 times a to the 6 times 1, that's a to the 6th. The next column, 6 times a to the 5th times 1 is 6 a to the 5th. I don't know, I just said times 1, times b to the 1, excuse me, which is b. Down the next column is 15 a to the 4th, b squared, then 20 a cubed, b cubed, 15a squared b to the 4th, then 6a b to the 5th, and finally b to the 6th power. Now if you think about how much work went into doing a binomial cubed, just imagine how much work would go into this binomial to the 6th power. So this method is a really nice, organized, concise, and much quicker way of expanding out a binomial. So this is the way I would really encourage you to use for binomial expansions. But there is one other way using Pascal's triangle, and we're going to just take a quick look at that on the next page. So let's turn to that page. Now this other method, which is really the method that, you probably more traditional way you'd see, or the way that is really focused more on in the textbook, is basically based on these ideas. First of all, for a binomial expansion of the form a plus b to the nth power, the following statements are true. Number 1, there are n plus 1 terms. So in other words, if you were expanding something out that was had a power of 3, you're going to get 4 terms. If it had a power of 4, it's going to have 5 terms, and so on. 2, the coefficients are the numbers from the nth row of Pascal's triangle. 3, the exponent of a is n in the first term, and the exponents decrease, like descend, by 1 in each successive term. That sounds like our table, right? 4, the exponent of b, which is the second term, is 0 in the first term, and the exponents increase by 1 in each successive term. And finally, the sum of the exponents in any term is n. So if you take the exponents of each one of the separate monomial terms and add them up, you should always get whatever n is, which was the original exponent. So using Pascal's triangle in a little different way, this is how we could expand out something like k minus 5 to the 3rd power. The first thing you do is you fill in those numbers from Pascal's triangle. So we have a power of 3, so we're going to use the row 1, 3, 3, 1. Then we take this first term k, and we start at the highest power of 3, and then we go down from there. So this is going to be k cubed, k squared, k to the 1st, and k to the 0 power. And then we go to the second term. We go to this negative 5, and we're going to go in ascending order starting at 0. So that's going to be negative 5 to the 0, negative 5 to the 1st, negative 5 squared, and negative 5 to the third. And now by multiplying these out, we're going to get our final binomial, or polynomial, excuse me. So if I multiply 1 times k to the third times negative 5 to the 0, negative 5 to the 0 is 1, so that's really 1 times k cubed, which is k cubed. Now the next term is going to be found by taking 3, multiplying it by k squared, and then multiplying it by negative 5 to the first. Negative 5 to the first is negative 5 times 3, that's negative 15, and then k squared. The next one is 3 times k to the first times negative 5 squared. Negative 5 squared is 25 times 3 is 75, so it's 75k to the first. And then the final term is 1 times k to the 0, which is also 1, and then negative 5 times itself 3 times, or negative 5 to the third. And that gives me a negative 125. So that is the expanded version of k minus 5 to the third power. And this is just using a little bit different method than the 3 separate rows. Instead, we just do it in one row, but we take into account all those same things. Number 1, Pascal's triangle. Number 2, the first term in descending order of powers. And number 3, the third term in ascending order of powers. So it's kind of based on the same concept, but with the 3-column table, it just seems to, for me, to be a little more organized. So I prefer that way. But of course, you could try either one. Now what we're going to do with this very last example is we're going to use this as an in-class example because I'm sure we're going to have some questions on this. So we're going to leave this for when we meet again, and so we'll go ahead and attempt this when I see you in class.